Now, in this part 1, I am going to deal with some basic definitions and basic concepts, and we are going to discuss the space R power n, the space R3, and we are going to learn about the point functions. Now, the basic definitions. What's a vector? A vector is a quantity which has both magnitude and the direction. What's a scalar? A scalar is a quantity which has only the magnitude but it has no direction. The examples of vectors are velocity, displacement, force, etc. A few examples of scalars are distance, speed, etc. Now we have to see examples of vectors and scalars in mathematics. Previously, I gave the definitions and examples in physics. In mathematics, what are vectors? What are scalars? Let us see. For that purpose, we have to learn the space Rn. Here, R denotes the set of all real numbers. Always we take real numbers as scalars because they have only magnitude. In mathematics, scalars means real numbers. Now, the space R power n is the Cartesian product of R n times. That means Rn is the set of all n tuples of the form x cap equals x1, x2, etc. xn, where each entry x suffix I is a real number. Now, these n tuples in Rn are also called vectors in Rn. How we can say x cap is a vector? To say it's a vector, it must have both the direction and the magnitude. How to assign direction to this vector x cap? The direction of this particular vector x cap is the direction shown by an arrow which is drawn from the origin 0 cap equals 0, 0, so on 0 to this vector x cap x1, x2, xn. The tail of this particular arrow is at the 0 cap and the head of the arrow is at the vector x cap. The direction of the vector x cap is the direction shown by this arrow. Thus, we assign the direction to the n tuple x cap. What is its magnitude? It is given by this formula. Norm x cap equals square root over x1 square plus x2 square plus x3 square plus so on plus xn square. Norm x cap is a real number. It is non-negative. It is called the norm of x cap or the length of x cap. It is the magnitude of x cap. So we assigned a length or magnitude and a direction to this x cap. So x cap is a vector in Rn. Now, how to add two vectors in Rn? If we take x cap equals x1, x2, so on xn and y cap equals y1, y2, so on yn in Rn, then their addition x cap plus y cap is given by x1 plus y1, comma x2 plus y2, comma x3 plus y3, so on, comma xn plus yn. This type of addition is called point-wise addition. Not only that, take a scalar alpha, that means a real number. Take a n tuple x cap, just multiply them. Alpha x cap is an n tuple alpha x1, comma alpha x2, so on alpha xn. This is called the scalar multiplication. So, we defined vector addition and a scalar multiplication in Rn. So, Rn is a set of vectors such that x cap equals x1, x2, etc. xn, where each entry xi is a real number in which addition of vectors and scalar multiplication is defined. Previously, we defined the addition of two vectors in Rn and the product of a vector x cap and a real number or scalar alpha, that is alpha x cap. These two are already defined. Now we are going to learn the dot product. The dot product is taken between two vectors. Suppose x cap equals x1, x2, so on xn and y cap equals y1, y2, so on yn, or any two vectors in Rn, then their dot product x cap dot y cap is a real number. It's a scalar. It is defined by x cap dot y cap equals x1 y1 plus x2 y2 plus x3 y3 plus so on plus xn yn. So dot product of two vectors is always a scalar. Now we can define the angle between two vectors in Rn also. If x cap and y cap are any two vectors in Rn, how to define the angle between those two vectors? Here is the formula. The angle between the two vectors, if it is theta, cos theta is equal to modulus of x cap dot y cap divided with norm x cap times norm y cap. So if we want theta, just send this cos to the other side, then theta equals cos inverse of modulus of x cap dot y cap whole divided with norm x cap times norm y cap. This gives the angle between those two vectors x cap and y cap. Thus we can define the dot product between two vectors and the angle between two vectors in the space Rn. Now we have to learn some terminology which is very useful in the further study of vector differentiation. Particularly, we must know what is meant by a unit vector. If x cap is a vector in Rn, if its norm or length is 1, such a vector is called a unit vector. So, a unit vector is a vector whose norm or length is 1. Now, what are orthogonal vectors? If we take two vectors x cap and y cap in Rn, they are said to be orthogonal if x cap dot y cap equals 0. That means two vectors are orthogonal if their dot product is 0. If we substitute this in our previous angle formula, cos theta equals x cap dot y cap divided with norm x cap times norm y cap, then what happens? Cos theta equals 0. Then what is theta? 90 degrees. So if two vectors are orthogonal to each other, that means they are perpendicular. That means they are perpendicular to each other, making 90 degrees of angle between them. Now, what are orthonormal vectors? If we take two vectors again, x cap and y cap, they are said to be orthonormal if first they must be orthogonal. That means x cap dot y cap must be 0. Next, their lengths must be 1. That means x cap and y cap both must be unit vectors. Their magnitude must be 1. So, orthogonal vectors are those vectors whose dot product is 0. Orthonormal vectors are those vectors which are orthogonal and their magnitude is 1. Let us see the space R3. R3 means our three-dimensional Euclidean space. R3 is the set of all three tuples or triplets x cap equals x1, x2, x3, where each entry is a real number. R3 is our three-dimensional space. In this space, if we take x cap equals x1, x2, x3, we have to assign a direction to it and a magnitude to it to call it as a vector. What is the direction of this particular x cap? As I previously said, we have to join the origin 0, 0, 0 to this x cap equals x1, x2, x3 by using an arrow. The tail of this arrow is at the origin and the head of the arrow x cap. The direction of this particular vector x cap is the direction shown by this arrow from 0 cap to this vector x cap. The magnitude or length of this x cap is norm x cap equals square root upon x1 square plus x2 square plus x3 square. This is called norm of x cap or length of x cap or the magnitude of the vector x cap. So we have assigned a direction and a magnitude to this point x cap. So it's a vector. Thus, each point in R3, each point in the three-dimensional space is a vector. We can add any two vectors in the three-dimensional space. If we take x cap equals x1 and x2, x3 and y cap equals y1, y2, y3, their sum is given by another vector x1 plus y1, x2 plus y2, x3 plus y3. If alpha is a scalar or a real number, alpha times x cap equals alpha x1, alpha x2, alpha x3. The dot product of x cap and y cap is x cap dot y cap is x1 y1 plus x2 y2 plus x3 y3. Already we have seen this in the space Rn. Now here particularly we take three vectors. I cap equals 1, 0, 0. This vector is a unit vector. Its magnitude is 1. And this vector is along the positive x-axis direction. J cap equals 0, 1, 0. This vector is also a unit vector and it is along the positive y direction. K cap equals 0, 0, 1. This vector is along the positive z-axis and its length is also 1. So these three vectors are unit vectors. What is a unit vector? A unit vector is a vector whose length or norm is 1. So all these three vectors are unit vectors. Not only that, we can observe a few points here. If we take the dot product between I cap and j cap, that is 0. Similarly, the dot product between j cap and k cap is also 0. I cap dot k cap is also 0. So here I dot I is 1, j dot j is 1, k dot k is also 1. That means these are unit vectors and also these are orthogonal to each other. Such vectors are called orthonormal vectors. So these three vectors are orthonormal because they are orthogonal to each other and also their lengths are 1. Now let us see how to represent a vector in R3. First of all, let us take a vector x cap equals x1, x2, x3. This is a representation of a vector in R3. We can represent the same vector in another way also. How to represent this vector? Let us see. Let us take x cap equals x1, x2, x3. We can write the same vector as the sum of three vectors. Namely, x1 0 0 plus 0 x2 0 plus 0 0 x3. This can be written as x1 times 1 0 0 plus x2 times 0 1 0 plus x3 times 0, 0, 1. Here, let us substitute I cap, j cap and k cap. Then the representation becomes x1 times I cap plus x2 times j cap plus x3 times k cap. The same vector x cap became x1 I cap plus x2 j cap plus x3 k cap. So, the same vector x cap has two representations. X cap equals x1 comma x2 comma x3, a triplet representation. The second representation is x cap equals I cap x1 plus j cap x2 plus k cap x3. This is called a linear combination representation. Usually in our lower classes, we see this particular representation x cap equals I cap x1 plus j cap x2 plus k cap x3. In our further lectures also, we use the same type of representation for vectors in R3. Point functions. These are very important in our chapter vector differentiation. There are two types of point functions. Vector point functions, scalar point functions. First of all, let us see what are scalar point functions. If we take a function f from an n-dimensional space Rn to the real number system, such a function is called a scalar point function. It is also called a scalar field. So it has two names, a scalar point function or a scalar field. Now, a vector point function means a function from Rn to Rm. That means a function from a multidimensional space to a multidimensional space. Such functions are called vector point functions or vector fields. For example, if we take f from R3 to R defined by f of x comma y comma z by using this formula, this function is an example of a scalar point function. Similarly, a function f from R3 to R3 given by this formula f of x comma y comma z is called a vector point function. So, vector point function, scalar point function are called point functions. These are very important in the study of vector differentiation. In this part 1, we have learned some basic definitions of vectors and scalars, and we have learned the space Rn. We have seen the space R3, the properties of vectors in R3, the orthogonal and orthonormal vectors, and we have learned about point functions. These are all very basics but very essential for our further lectures on this vector differentiation. Thank you everyone for listening.